There are 4 simple steps. First, we need to define our functional building blocks. In our example, there are the state preparation for A, the state preparation for B, and the adder itself. Next, we define the high-level functional model. Then, we wire our building blocks into the model. Lastly, we need to define how to execute the quantum algorithm. In other words, define what we want to do with the quantum algorithm. Do we want to sample the output, or do we have parameters we want to optimize in a hybrid way? In this example, we just want to sample the output and receive some histogram of the measurements. Okay, so let's open our Python notebook and the tutorial itself side by side and do it together. We start with step 1, where we define the building blocks. Firstly, we define the 2 state preparations we have. We first define probabilities of the states we want to generate, and then we define the 2 state preparation building blocks. For each of them, we input what probability vector we want to prepare, and what is the error bound we allow. Next, we initiate the adder object. We need to define what is the size of the adder input register as the left and right arguments. That's all we need for step 1 of defining the building blocks, and we can now move to step 2 where we define the model. It is simple. We just initiate one instance of the model object. The third step is to wire our building blocks into the model. First, we wire the state preparation objects into the model with the corresponding building blocks we defined in step 1. We call the outputs of the wiring A and B correspondingly, while we are using them as the inputs to the wiring of the adder itself. The last step, step 4, is to define the execution scheme. In Classiq, the sample execution scheme measures all relevant qubits and produces a histogram. In order to apply the execution scheme, just write model.sample. That's it. Now the Python object called model encapsulates everything we need about our algorithm. However, the input to Classiq synthesis engine is a model in a different format called QMode. This QMode is just a text file describing the entire model in a way the synthesis engine can understand. So, in order to generate our circuit, we need to transform the Python model object into a QMode. This is done with a getModel method. Now we have our QMode. These kind of QModes, which are the input to the synthesis engine, are exactly what we've seen in the IDE. Now we finally understand how we can generate them. In the next video, we will complete our understanding of how to work with the SDK, and we will cover all the interfaces between the SDK and the IDE.
Welcome to part 2 of lesson 4 of the Classiq bootcamp. In the last video, Tali showed us how we can build models with the Python SDK, and we finished with having a QMode, the model in format that enters the Classiq synthesis engine. In this video, we want to review how to make the connection between the Classiq IDE and the Python SDK, and to understand what these interfaces are. So let's get started by going back to where we finished in the last video, and this is with the QMode itself. The first thing we can do is to copy the QMode we have received, which is just a text file the synthesis engine can understand, and to paste it in the synthesis page of the Classiq platform. These are the models that we've been seeing for the last few lessons in the IDE. After synthesizing the model, we receive the quantum circuit we wanted. We get 2 state preparations and the adder. Great, so this is the first interface between the Python SDK and the Classiq IDE. Just copy and paste, the simplest way that can be. There is another way of interfacing the QMode from the SDK to the IDE, and it's done by saving the QMode as a file, uploading it directly to the synthesis page. This is done by firstly saving the QMode into a file in our notebook. Then, we need to get access to the file itself by downloading it locally to our computer. Now in the synthesis page, we have a button for uploading a QMode. We just select the QMode, and we have our QMode in the IDE, just like copying and pasting. Now we can synthesize the model, and as expected, we receive the same circuit. So these are 2 ways of loading the QMode from the SDK to the IDE. Now I want to continue one step further within the SDK and to synthesize the model directly within it. This is done by inputting the synthesis function in Python and then synthesizing the QMode. The output of the synthesis is the quantum program, the QProg, which contains the circuit itself in addition to other things like the execution scheme of the model. But it's not very indicative to view it like this, as a string, so we have again 2 ways of interfacing with the IDE. First, we can directly open the circuit contained within the quantum program with the function show. This will give us a link to the platform where we can view the circuit as if we synthesize it directly within the IDE. Another way of interfacing the quantum program is by saving it into a file and directly uploading it to the IDE, as we did before with the QMod. For this, we need again to have a local access to the file. Now, when we go back to the platform, to the circuit page, we have a plus button next to the circuit names. Once we click on it, we will have the option to drag and drop our quantum program or to upload it. Then the quantum circuit, which is contained within the quantum program, can be opened and viewed as usual. So to summarize, we have seen two ways of interfacing the QMod from the SDK to the IDE, either copying and pasting in the synthesis page or saving it as a file and loading it. And we've seen two ways of interfacing the QProg, which contains the circuit, with the show function, which opens a direct link to the IDE, or by saving the quantum program as a file and uploading it to the circuit page. Two additional points before we finish the session. To the circuit page, you can also directly upload CASM files. So if you're working with Qiskit, for example, and you want to use Classiq for visualizing the circuit or for executing it, you can directly upload CASM files, which is really nice and useful. The second thing is that when working on long projects, it might be convenient to save both the QMods and the QProgs while you work. And this way you don't need to resynthesize your models or to generate new models each time. You have all your files ready and you can return to the point you stopped working at with one simple click. Thank you. Welcome to the last video of the Classiq Bootcamp. In this final episode, we want to touch on a more advanced topic that can be really useful for the Classiq hackathon. This is how to incorporate some parameters into our models. We will review two possibilities, two execution schemes. The first is the sample execution scheme. This is the regular measurement and histogram we expect to receive from the execution of a quantum circuit. We will design our model with some parameters, and only when we code the execution scheme to the model, we will pass the parameters. The second is a hybrid execution scheme, called the VQE. It is originated from the variational quantum eigensolver algorithm, which we reviewed in a previous session. We will use it as a general variational scheme, where we will design our model with some parameters and ask Classiq to optimize these parameters according to some loss function. So let's start. Our example for both execution schemes will be a simple RY rotation over one qubit. First, we initiate our model. Then, we define our building block, which is the RY gate in this case. This gate expects to receive one parameter. And now we will just define the parameter as a string. This will be our variable. Next, we need to wire the building block into the model. And finally, we need to define the sample execution scheme. Here, however, we need to pass to the execution scheme what are the parameters the model should synthesize it with. So we define our execution parameters as a dictionary, where the keys, or the key in our case, are the parameters themselves in the form of strings. And the values of the dictionary are the values we want the model to substitute, pi over 7 in our case. Then, we define the execution scheme to be sample, as usual, but now we pass to the model the execution parameters to be substituted. And that's it. Now we can continue as usual and to synthesize the model, and even to execute it and review the results. So this is the first way to pass parameters into the model. This can be useful if we have some pre-processing to do, some intermediate calculations, or a loop where we want to substitute many parameters within. Let's go ahead to our hybrid execution scheme now. Firstly, we define the RY building block and wire it to the model as before. We still pass it the parameter in the form of a string, and we call it x as before. Now comes the cool part. Instead of just sampling the generated circuit, we set the execution scheme to be a VQE. The first thing we need to pass to the VQE scheme is the Hamiltonian we want to minimize its energy, or we can view it as our loss function. We need to pass the Hamiltonian we want to minimize in the form of Pauli list. In our example, we choose the Hamiltonian to be a sum of the Z and X Paulis with the coefficients 1 and 0.1 respectively. Here we can see the Hamiltonian's matrix representation. Next, we need to define in the VQE scheme what's the maximum number of iterations we want to have for our hybrid model. Lastly, we need to choose our classical optimizer. And that's it. Now we can synthesize our hybrid model, execute it, and view the results. Specifically, we can see what is the optimal parameter, which is the optimal angle of rotation for minimizing the Hamiltonian we chose. This brings us to the end of this video, to the end of this lesson, and to the end of this first Classiq Bootcamp. We hope you enjoyed it so far, and that now you have the capabilities to master the Classiq platform.